Hello, welcome to section 11.4, and in this section we are going to look at population dynamics. We're going to pick up where we left off last time and ask ourselves a question: what would happen if we removed all limiting factors? What would happen to the population? We're going to look at a couple of different growth curves and growth models, exponential versus logistic. Didn't mean to move the frame there. Exponential versus logistic growth. We're going to look at population density. What does the term carrying capacity mean? And several different population cycles, boom and bust, and predator-prey. So let's revisit that question. What would happen if we were to take away all limiting factors? Well, let's look at that with a population of bacteria. Let's say we start with one single bacterial cell in a really huge container of nutrient medium, has all the space it needs and all the nutrients it needs. And let's say that cell and any descendants from it, they divide every 30 minutes. How many cells would you expect to find in the container in 24 hours? If you want a little bit of advanced proficiency, why don't you show me the math on this? But I will tell you how many it does provide, and that would be 280 trillion bacteria in just 1 hour. That's the result of starting with only one bacteria that divides every 30 minutes. So if we are to take that information and graph it on a graph, that graph looks like this. It is called exponential growth. It is the growth that can be seen in completely ideal circumstances where limiting factors are not limiting the growth. Now, a more realistic growth model would be this one, logistic growth. In the logistic growth model, you can see that the curve begins in the same way that our exponential growth curve began. It looks the same here, but when the population begins to encounter some of these limiting factors, maybe nutrients or other resources are used up, maybe there is an increase in death rate due to disease or any number of different factors, that population growth pattern begins to slow. It reaches this logistic growth curve because of those limiting factors in the population. That brings us to another topic, population density. What is population density? Population density is simply what it is, the number of individuals per unit of land area, or in the case of aquatic environments, it would be the number of individuals per area of water volume. And here you could see the density is fairly uniform. You could count the number of individuals, count the area that you're looking at there, and you'd have your population density. Here, this is quite a dense population in that area. Population density, as it increases, will cause competition within the population because nutrients and other resources are used up. Here's a map and several graphs that show human population density. This one shows, obviously with the darker the colors, the more dense the human population is in those areas. Here's another graph representing over the years, fairly recent years, the billions of people in the world population, and the green shows that population in developing countries, and the yellow is showing in industrialized countries. Those are pretty different. This is the projection out to 2060, it looks like, or 2050. Here is another graph showing human population levels through history. What kind of growth curve does this look like? Does this look like exponential or logistic? So far it looks exponential. Remember, the logistic growth curve begins that way as well. This is just an interesting graph to look at. Here is where the plague occurred. You can see that there was a population decrease right there. There's the Industrial Revolution, and you can see that population density has increased dramatically very recently in the overall history of recorded history for human population. That brings us to an important term in population dynamics, and that's called carrying capacity. What is carrying capacity? Carrying capacity is the largest population of a species that the environment can support. And if we go back to our different growth models here, it's the carrying capacity right here that is limiting the growth of this population and causing this exponential growth to turn into logistic growth right here. That is the carrying capacity. So when you start to hit these numbers right in here, you know that the population has reached its carrying capacity. It can't support any more of those species in that environment. Here's just a little diagram showing, if we think about this carrying capacity as being the top of this bucket here, you can see that some factors are reducing the population. We have predators are reducing the population. You have populations rising up here, but predators will reduce it. Starvation reduces the population. Disease will reduce this population. There are population losses sort of draining out the bottom. Hunting will certainly do that. We have accidents or pollution to reduce the population. Here would be habitat. Habitat, if you have plenty of habitat, we can have more growth, more population growth, because habitat is one of those limiting factors. If you have more of it, you can then support more species of that population. Now, that brings us to another point. Is carrying capacity fixed? Is it always the same in a given environment? No. It can definitely change. There could be changes in food supply, changes in other resources that can increase the carrying capacity or decrease it. For example, carrying capacity for humans, artificial fertilizer enabled an increase in the population size of crop species. So that increased the carrying capacity. So a lot of different factors affect carrying capacity. So populations do not always follow the nice, neat little logistics curve, just as tidy as it has appeared in our graphs here that I've shown you. Sometimes populations show more extreme cycles. Here would be an example, a boom and bust cycle as an example of that, where perhaps we have a population that it grows rapidly and it exceeds its carrying capacity here, and therefore it enters into a phase in the cycle where there is a high death rate, a huge sharp decrease in birth rates and reproduction, and you end up getting a crash on this side. Then it goes back into that exponential part of the growth curve, exceeds its carrying capacity, and crashes once again. That's called a boom and bust cycle. Another example of this would be the predator-prey cycle. We have this boom and bust of the prey, the rabbit in this case, but predators that rely on their prey for their resources, their population cycle will be greatly affected as well. And you can see how as the rabbit population exceeds its carrying capacity up here, it allows the fox, or whatever the predator happens to be, that population will rise as well and peak here as the prey population starts to plummet and crash on this side, and the predator population then follows that a bit here. And you can see how the predator-prey cycle, the predator cycle follows that prey cycle as well. It's called the predator-prey cycle. So some main points to remember in this. Types of growth, exponential versus logistic. What does that look like on a graph? And see if you can think of how to explain that. Population density. What is that? How does it affect populations? What's the carrying capacity? And our different cycles are boom and bust cycle, and then the predator-prey cycle. Some advanced ideas are right here. Did you know there is a nice mathematical formula for the population rate of increase? You can look into that. How do you use it? What do the different letters in that formula mean? What's the difference between R and K selection? Look into that and how that relates to density dependent and density independent factors in a population. And I look forward to seeing what you come up with, and we'll see you in class.